All right, so one of the things we look at is equipotential lines. You'll be oftenly asked to look at this. And basically, an equipotential line, it just means equal potential. Okay. Obviously, the potential just becomes a potential. So, whatever. I didn't really add any value into there, but it just means where the potential is equal. And because and the whole idea on an equipotential line is everywhere along, this might be an equipotential line, everywhere along it's the same potential. And so what ends up happening is if you move at any point along there, along this line, is going to have the same potential. Remember, we use the potential to talk about the change in energy and potential energy and things like that. Now, couple of things that we're going to derive here based on it. Relationship to the electric field. Because work is related to force, we can relate the electric field to the electric potential, and it's derived from our work energy principle. So let's kind of think about like why that is. Okay, so remember the work we do is going to be Q times delta V, like this, right? And then this is depending on if you're doing the integral form or the differential form. It's a force times the displacement equals Q delta V. Or for those of you in AP Physics C, it's the integral of the work is going to be that Q times that change in potential energy there, like that, right? Now because of this force also being Q times the electric field, you can do Q times the charge that you put there, right? Times the electric field is the force that it experience. So the Q's cancel, and you get this relationship. The electric field is the change in potential divided by the displacement. All right, so if I pick 2 points along here, and I look from here to here, the difference in the potential divided by the distance is the electric field there. And on the integral form, you do the exact same thing. It's Q. It's just more differential form. It's integral Q times the electric field dx is equal to Q delta V. So then those cancel, so you get this form. Or you sometimes see the derivative, the differential form being the electric field is the derivative of the potential there. Okay. There's technically a negative sign because this is potential energy. The work is the negative change in the potential energy, but I would not worry about that too much. So there's technically a negative sign in there. Not a huge deal. I usually, again, use the sign of the electric field. I usually just focus on the magnitude and don't think about the directional part, but technically there's a negative sign in there as well. Okay, so basically the way you want to think about the electric field, it points, so rather than using the sign of this, I really look at as saying the electric field points from higher potential to lower potential when you're having the electric field lines. And the whole reason, and it's perpendicular to it, by the way, and the reason it's perpendicular is because when you move along the equipotential line, it means the electric field is not going to do any work. And that's because if you move along this line, you'll be moving in a displacement that's perpendicular to the electric field. So there's no force or no work being done by the electric field there, right? Because they're perpendicular. You need to have a parallel component. So the electric field ends up being perpendicular to the equipotential lines, and it points from higher potential to lower potential in general. So these are lines where the potential is the same. It means it takes no work to move the charge from one point to another. So you can see here the blue lines are the electric field lines, and the dashed lines are the equipotential, and it makes perpendicular lines there. Okay, because there's no work to go from there to there because the electric field is going to be perpendicular and is not, even though it exerts a force, it's perpendicular to the motion. If you want to review work and energy or calculating work, that's where that comes from. So let's kind of do some example problems of where you would kind of see this happen. So the diagram shows some equipotentials in a plane perpendicular to two parallel charged metal cylinders. The potential of line is each labeled. The left cylinder is charged positively, so we know that this is positively charged. What is the sign of the other charge? Now, let's think about the direction of the electric field. How do I know this is positive charge? Well, the electric field points from higher to lower potential. So that means it's pointing in this direction because it's 10 volts, then 0 volts, then negative 10. And remember, for a positive charge, the electric fields point away. Now, what's the direction of the electric field here? Well, it's going from higher potential to lower potential, so the electric field is going to point like this from higher, because it goes from 10, 0, negative 10. The electric field is going to point that way, and it's also going to be positively charged. Positive because you can see the potential is decreasing, which means the electric field is moving away from the charge, right? Like a positive charge. On the diagram, the direction of the draw the direction. This should say draw the direction of the E fields at point A, B, C, D, and E. So again, it's perpendicular to the surface and points to lower potential. So for A, it's going to be perpendicular and like this, right? And pointing to lower potential because this is higher potential here. B, let's see, this is higher potential, this is lower potential, and this is even lower, so it's going to point this way. C, it's going to point this way. Again, make a right angle. D, it's going to point from higher potential to lower potential that way. And then E is going to be this way. And again, all of them need to make this right angle perpendicular to the equipotential lines. Determine the potential difference VA minus VB between points A and B. Well, so VA is negative 20 volts. So that's going to be it's going to be negative 20. And then VB, if you look at this line here, is negative 10 volts. So when you do VA minus VB, it's going to be negative 20 minus negative 10. And that's going to be negative 10 volts there. How much work is done by the field if a charge of 0.5 coulombs is moved along a path from point A to E and then to point D? So all that matters, this is the awesome part of the potential, is if we think about the work being done, it's going to be Q times the change in potential. Now, that's going to be the work done by the electric field. Yeah. So we're going to take that charge and we're going to take it. What's the potential difference between VD minus VA, right? And so we're going to take VD, which is 10 volts. VA is negative 20, so it's going to be 0.5 times VD, which is 10 minus negative 20. And that's going to be 30 times 0.5, and that's going to be 15 joules. Now, I always because of all the signs and things like that, I try not to rely on the formulas. I want to think about myself, is this positive work or negative work? And go back to that fundamental unit 3. Work is positive if the force and the displacement are in the same direction. So if we're going to go from A to D, okay, ultimately, right, the electric field is going to be opposite the direction of the displacement there. So it should be negative work here. And that's why there is that negative sign in there that I kind of left out. So it's going to be negative 15 joules. But I tend to think of it that way. You can use the signs as long as you're very clear on the signs. I think signs is one of those things that's really easy to forget. So I like to rely on first principles to help me remember that if I can't recall in that moment. I try to think about first principles. When is work positive? When is work negative?